Welcome back to this YouTube tutorial series on numerical methods in Python, and in today's video we're going to be going over the bisection method. So to begin, we're going to actually go over exactly what root finding means. Root finding simply means an algorithm for finding the roots, better known as the zeros of a function. So here we have an example. Find the roots of x squared equals 4. We can better adjust this function as the following. We can take 4, subtract it by both sides, and we get x squared minus 4 equals 0. So root finding simply means at what values of x does this equation equal 0? The answer is f of x equals 0 at x equals negative 2 and 2. And so now we know the importance of root finding. How do we actually implement this in an algorithm for a computer to solve? So to begin with, we were given the bisection method, also called the binary search method. It is based off of the intermediate value theorem. The intermediate value theorem is the following. If f is a continuous function on the interval a to b, and n is any number between f of a and f of b, where f of a does not equal f of b, then there is a number c in a to b such that f of c equals n. So what this exactly is saying is we're given a function f. Here we have our function f. It is continuous on the interval a to b, where a to b is our interval on the x-axis. Then there exists some number n, that is any number between f of a and f of b, where f of a and f of b are on the y-axis. So n is some y value, where f of a does not equal f of b. Then there exists a number c in between a to b, where c is an x value, such that our function of c equals n. And so any value c between the x values a to b is going to be equal to some y value n, where n is between our f of a and our f of b on the y-axis. This is a very important fundamental theorem for finding the roots of a function. And so before we begin exactly on the bisection method, I'm going to give a simple binary search example. So here we have a list. This is going to be in Python. We were given a Python list with values 1 through 6. And we're given a my value 3. And we're going to perform 2 iterations of the binary search method. So is my value present in the list? So in iteration 1, what we do here is we have our first index 0, where the first index, where index refers to the array. And so because Python is 0 indexed, our first index is 0, not 1. So we have our first index 0, the 1. We have our last index 5, which points to 6. And what we do is we calculate the middle index. So we take our last plus our first indices and we divide by 2. And I'm rounding up here, so we get 5 plus 0 divided by 2 is 2.5. We round up to 3. So now we get the value at index 3, which is 4. And we're going to say, is our value we're looking for, is it less than or greater than this value? And in this instance, it's less than. So now what we do is we actually partition our list into another part, where we subdivide it into a smaller degree. So now what we do is we leave our first index the same, but we adjust our last index equal to the third index. So now what we do is we shrink our list by cutting off these last 2. So now we're given the first index of 0, the last index of 3. The middle index, now we calculate it again as 3 plus 0 divided by 2. We get 1.5. We round that up to 2. So now we have a value at index 2. And our value is actually equal to the value we're looking for. So this procedure of subdividing subdividing our list by halves is known as a binary search. And that is exactly what we're going to perform here in the bisection method. So because of the intermediate value theorem, we know that this root has to exist if it's between our f of a and our f of b. And this only occurs if we choose our interval carefully on our function. We have to choose we have to choose a and b, our interval, such that f of a times f of b is negative. So let's say if we were given an interval a and b, and we choose this value here and this value, these two values times each other are positive. Therefore, there's no way there's a root. So we have to choose our interval where the signs are negative between our function evaluations. And so here I'm going to bring up a quick picture. I'm going to adjust this as so. So here we have an example. Let's say we're given the function, once again, x squared minus 4. We choose our interval as such. We choose a to equal 3 and b to equal 0. So we choose our interval a and b. Now what we do is we find the median value, the middle value. So we take a plus b and divide that by 2. So we have a plus b, divide that by 2, we get negative 1.5. All right, and now what we do is we're going to set this as a label. So here we have our f of m. Our middle value is negative 1.5. As we can see here, a times m is negative. And so what we do here is we adjust our b equal to m. Hold on, let me back up real quick actually. So here in our binary search list, we have a way of comparing values. That is simply by comparing integers. We say is 3 less than 4, then proceed. But how do we compare here? What we do here is we compare by the function evaluation signs. So we say if f of a times f of m is negative, then our root is in between this interval. Now if f of a times f of m is positive, then our root would be in between the interval of f of m and f of b. And we'll eventually get to that occurrence as we keep on going through this example. So now what we do here is we adjust our f of b equal to our f of m. So f of b2, we adjust our b equal to b2. What we do here is we calculate our new middle value between f of a and f of b2. And that is negative 2.25 here. So here we have f of m2. As we see here, f of a times f of m is now positive. Therefore, our root is in between f of m2 and f of b2. So what we do is we adjust our a equal to m. So we set our a equal to m. We get our new a value. So now we have f of a2 and f of b2. We calculate the m value again. So here we have f of m3. Let me get these extra ones out of the way. So here we have our middle value again, and f of a2 times our f of m3 is negative. Therefore, we must adjust our b equal to our m. So we do that again. So we have f of b3 here again. And so now what we have to do is we have to find our middle value again. So our middle value is a2 plus b3 divided by 2, and we get this. So this is our middle value. And then simply again, we keep on repeating this procedure back and forth, and we keep on shrinking until we approach the root. And the way we do that is, eventually, our f of a and our f of b are going to become so close to each other that they're basically going to equal the root. And what we do is we compare these two values to a tolerance level. And so that is simply the bisection method in terms of a given example. So now how would we actually implement this in Python? So what we're going to do here is we're going to have some argument types. We're going to be given an interval a to b, maximum iterations n, and the reason why we're giving a maximum iterations is simply because let's say we were to choose f of a to be where it is right now and f of b to be some positive value. Then we're going to keep on iterating in this infinite loop as there's no root. So we want a maximum iteration to break out of the loop, or let's say our function is derived in such a way that it would take over 1,000 iterations just to find the root to a given tolerance. And so the sufficient number of iterations needed for a given tolerance is calculated by the following equation, without proof of course. The natural log of b minus a, which are our interval givens, minus natural log of c divided by natural log of 2. I meant to write tolerance here, not c. So the natural log of b minus a minus the natural log of our tolerance, and divide that all by 2, and that is at least the number of iterations we need. And so now let's actually implement this in Python. So we're going to say definition, bisection. We're going to give it a function to use, our a or b, our tolerance, and our max iter. What we're going to say here is we're at this first check off, is f of a times f of b negative? Because if we give it, let's say this f of a2 was our b, there's no root in between these two values. So we're first going to have to say if function of a times function of b is, if it's positive, then we're going to print out error, function requires a change of signs over the given interval, and we're just going to return -1. So before we begin, we're going to keep track of our current iteration count. We're going to say while true, we're going to set our m, our middle value, is equal to a plus b divided by 2, and then we're going to say f of a is equal to a function of a, f of b is equal to function of b. And remember, what we have to check to see is our f of a value times our f of m value positive or negative? We're going to say if f of a times f of m is negative, that means we need to adjust our b value to equal our m value. So b is now equal to m. Elif our f of a times f of m, oh, excuse me, this needs to be f of m, not f of b. If this is positive, then we need to adjust our a value to equal our m value. Else, this would only occur if f of a times f of b were to equal 0. And this would be a break. We would simply break from this statement. And we're going to update our iteration. And now what we do is we need a stopping condition to make sure we don't have some kind of infinite loop. So what we do here is, as I stated before, as we can see here, our f of a's and our f of b's slowly approach the root. But eventually, they're going to keep on approaching to where they become so close that if we minus their values, we need to check if that is less than our tolerance level. So we're going to say if the absolute value of b minus a is less than tolerance, we're going to break. Else, we need to check if our iterations has reached the maximum iteration count. We're going to print max iterations reached, return -1. And then we're going to return m, where m is going to be the value in between a and b. So there we have it, our simple bisection method. We're going to define a new function. We're going to give it an x value. And we're simply going to return x raised to the second power. What did we say here? -4. And so now what we can do here is we can say x, or our root, is equal to bisection of our function. Let's give it an interval. What did we give it here? We gave it -3 and 0. So it goes a first, -3 and 0, a tolerance of 1e to the -8, and let's say 30 iterations. Now, unfortunately, this is all the time we have left for today, so please stay tuned for part 2 of this series.